Okay, happy Friday, everyone. I hope you're all doing well. So announcements. There is no homework due today. The next homework is due on Friday. And Friday is going to be, next week will be Good Friday. So there's obviously no classes. So if you don't want to be doing homework on a holiday day, just get it done the day before by Thursday. And then the only other thing I was going to, I guess there's two other things. We're going to be doing the last lab next week. So lab 8 next week will be the last of the Phys 121 labs. And there is a pre-lab, so please get that done before your lab section. And then the last thing I was going to say was that if you signed up for the hands-on bonus project, this is just a reminder that you have to send me your YouTube link by April 8th. So that's just that's at the beginning of the last week of classes. Okay, and then here is the distribution of the quiz 2 results. The average was 64. So that's basically identical to the average from quiz number 1. But 28% of the class got 8 out of 10 or better. And so that's a pretty good result. Okay, good. So if you haven't noticed already, I did post the solutions to quiz number 2 on the course website. So if you want to have a look at any of my solutions, they are available. What we've been talking about before the quiz was the fact that moving charges or currents create magnetic fields. And we first thought about a single point charge Q moving with velocity V. And if we wanted to know the magnetic field at point P, we had to calculate it in a little bit of a more complicated way. It involved this cross product, the V cross R hat. And so it's this funny result that the magnetic field direction will be perpendicular to both the velocity vector and that position vector R. So if those two vectors are in the plane of the screen, the magnetic field will have to be either out of the screen or into the screen. And how you determine which it is the right-hand rule. So you put your right arm in the direction of the first vector in the cross product. In this case, it's the velocity. You curl your fingers so that they're parallel to the second vector in the cross product. So that's R hat. So it's kind of tilted slightly upwards. And then your thumb gives the direction of the magnetic field. And so in this case, the magnetic field would be coming out of the screen. And so we would indicate that with like the tip of an arrow coming out towards us. All right. And then we said, well, typically when we have moving charges, a common way to do that is to have a current in a wire. And so we recast this expression to be not in terms of a single point charge, but in terms of a little segment of current of length delta L. And so I've drawn a wire carrying a current, and I've highlighted a little segment. I colored it red. And so if we wanted to calculate the magnetic field due to just that red little segment, it would be given by this so-called Biot-Savart Law. So in general, we wouldn't really want to know the magnetic field just due to one little section of the wire. We'd want to know what is the magnetic field at P due to the entire length of the wire. And so to do that, you would divide the wire. Imagine dividing the wire up into a bunch of short little segments of length delta L. Then you apply the Biot-Savart law for each of those segments, and then you add them up as vectors at the end. And so that's what you'd have to do. And we're going to do an example of that today. The other thing that we noticed is that if you had a loop of current, it creates a magnetic field that looks very similar to the magnetic field that you get from a bar magnet. And so in that way, these little current loops are going to serve as kind of approximations to bar magnets. And that's just useful to have in the back of your mind when you encounter different geometries of currents. So for example, in lab 7, you use a solenoid, and you could think of that as a bunch of little current loops lined up in a row. And the magnetic field is due to the magnetic field at some position, say inside the solenoid, is due to the sum of all of these current loops. Okay. And in fact, what we're going to do today is we're going to use the Biot-Savart law to try to calculate the magnetic field at the center of a current loop. So we'll draw our current loop again. So I'll draw it like this. And we'll pick a direction. We'll use the same direction as drawn above. And so here's some current. And maybe we're going to be interested in what is the magnetic field due to this section of our little loop of wire. And so we'll say that that section has some length dl, and we can make the dl vector delta L, sorry, vector, something like that. So that's, yeah, that's not the best. That looks like it's pointing upwards, but I'm gonna draw this somewhere else so that it looks a little bit better. So let's pick a little segment over here. And so this has a length delta L, and we can draw the delta L vector like that. That looks a little bit better. And what we're going to be interested in is finding the magnetic field at point P in the center of the loop. So P is in the center of the loop, is at the center of the loop. And we want to find the magnetic field at the center. Okay, let's just write down the Biot-Savart law again. So there it is. Mu naught over 4 pi I delta L cross r hat divided by r squared. So from the Biot-Savart law, B at P due to the blue section of the current loop is given by, okay, so it would be, say, BI, if that's little segment I, is going to be, the constant out front was mu naught divided by 4 pi. And then we had this I delta L cross r hat over r squared. So there's one thing missing from our picture, and that is that position vector r. And so I can draw the position vector, and it is going to look something like this. There's r, and r hat is just a unit vector that is in the direction of the position vector r. So what I want to do is I want to redraw this picture, but we'll draw it from as if we're looking down on the loop. So let's redraw this picture and we'll do a top view. So if we're looking from above, our loop looks like a circle. Okay, and let's see, from above, the current would be going counterclockwise, and so I'll draw the counterclockwise current. There's I. P is sitting right at the center here. We'll make our little blue delta L section here. So here is delta L, the length of the segment. The delta L vector, we drew it red, and so there it is, delta L vector. And then the position vector, we drew green. There it is. And then we had finally our r hat unit vector. All right. So what I want to focus on first is trying to evaluate this cross product that we have to deal with, this delta L cross r hat. So let's first consider delta L cross r hat. All right, so we'll start with the magnitude. So the magnitude of delta L cross r hat. So remember, for cross products, if we want the magnitude, it's the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. So it's going to be the magnitude of delta L times the magnitude of r hat times the sine of the angle between them. What's the angle between delta L and r hat? 90 degrees, okay? So this is going to be 90 degrees. What if I had chosen a different position for our little current segment, right? Maybe I could have chosen it at the right edge of this loop. What would the angle then be? 90. No matter where I put my little current segment, in this geometry, the angle between delta L and r hat is always going to be 90 degrees. Okay, sine of 90 degrees is 1. The magnitude of a unit vector is 1. And the magnitude of this delta L is just that length, delta L, whatever that is, its scalar value. And so all of this just evaluates to delta L. All right, so let's do the direction of delta L cross r hat. All right, so the direction is going to require that we do the right-hand rule. Remember, for cross products, the result of a cross product is another vector, and that vector has to be perpendicular to both delta L and r hats. That should be at r hats. I should have r hats here. Let's fix that. So if the result of that cross product is perpendicular to both of these vectors, it has to be either out of the screen or into the screen. So all we're doing with the right-hand rule is trying to determine whether it's out of or into the screen. So remember, the right-hand rule says, put your arm in the direction of the first vector in the cross product. In this case, it's delta L, and it has to be your right arm, of course. Then curl your fingers so that they are in the direction of the second vector. That second vector is r hat. It's kind of sloped down a little bit. And so now my thumb is pointing into the screen from this perspective. And so delta L cross r hat. I'm getting, oh, I've done something dumb. What have I done wrong here? What should the direction of delta L be? Should it be, we define that to be in the direction of the current, but I did something stupid. I drew my delta L in the clockwise sense, but my current is going counterclockwise. So that doesn't work. So let's see if I can fix this. So we'll see, we'll draw our loop back here. We'll color in our blue section. And now I got to put my delta L so that is in the same kind of orientation as the current. Okay, so everything, the magnitude calculation doesn't change, but our cross product changes. So now what I have to do is my right-hand rule again. Now, delta L is kind of sloped downwards, and r hat is kind of sloped down as well, but towards me. And now my thumb points in out of the screen direction. So by the right-hand rule, delta L cross r hat is out of the screen. Okay, so then we could go over here and we could say, well, okay, the magnetic field is going to be out of the screen at P, so we'll draw that little arrow tip coming towards us. All right, so the last thing we need to do is if we want to find the total magnetic field, we just have to go and plug all our results into the Biot-Savart law. And so B due to current segment I is going to be the mu naught over 4 pi is the constant out front. We have a factor of the current. And then we said the magnitude of the cross product ends up just being delta L. And we still have an R squared in the bottom. And we have determined that this is out of the screen. So this is due only to the blue current segment. So if we want to find the net magnetic field, we have to do this calculation for all of the little segments that would be needed to form that complete loop. So B due to all segments needed to form the complete current loop is, okay, so B is going to be equal to the sum of all of these little current loops BI. All right, let's go back to our picture and let's draw a second little segment of current. So there's one over here, and we would have now a delta L. Let me get the direction correct, would be something like this. The position vector would be the vector that goes to P. And so we would have another position vector over here. If I did the cross product, okay, so let's see. I assume I've lost the Wi-Fi on this thing as well. Super. Okay, so UBC secure. Let's do visitor. Okay. Okay, did it? Yeah. Well, I am connected now to visitor, so we'll see if this works out for us. All right, so what we were saying is that all current segments in the loop contribute magnetic fields that are out of the screen. Okay, so that means really, since they're all in the same direction, they're just going to add up normally. And so really what we're focused on is finding only the magnitude of the magnetic field. So the net magnetic field will have a magnitude equal to the sum of the magnitudes of all the little segments. And we know that each of these segments are going to contribute a mu naught over 4 pi times the current times delta L divided by, say, Ri squared. But if we have a loop of current, then wherever we are on that loop, we're always the same distance from the center at point P. The Ri is the same for every single current segment. So since all segments are the same distance r from P, we could say that the net magnetic field is the sum of mu naught over 4 pi I delta L over R squared. We don't need a subscript if all of the lengths, all the radii are equal. Okay, to make this result exact, what you would do is you would shrink your current segments into these tiny short little pieces and add up many, many, many of them. So in the limit that delta L goes to 0, the magnetic field would be the integral of mu naught over 4 pi I, and then the delta L for an infinitesimal length, we'll write that as dl r squared, and then we have to integrate around this loop. But almost everything in this expression is a constant. Mu naught and 4 pi are obviously constants. The current is the same everywhere on the loop, so it's a constant. The distance from the loop to point P is the same everywhere, so r is a constant. We can factor all of that stuff out. And so this would be I over R squared. We have the integral around the loop of dl. So the integral of dl is just adding all the little segments, all their lengths around that full loop. And so if we add up all those little lengths, what do we get? You get the circumference, and the circumference is 2 pi r. Yeah, so the total length of the loop, that's right. So the magnetic field at the center of a current loop is given by, let's see, B is mu naught over 4 pi I over R squared, and then we have to multiply by 2 pi R. And so we have some cancellations. One factor of R cancels, the pi cancels, and then we have a 2 over 4, which becomes a 1 over 2. And so the final result is the magnetic field at the center of our current loop is mu naught I divided by 2R. And so if we draw our current loop again, so here's our loop of wire. And let's see, I'll draw my current going this direction, and the resulting magnetic field at the center looks something like this. So here's the center point is right there. All right, so we have to just be careful is that this is valid only at the center of the loop. If we're in the plane of the loop but off center, the magnetic field will change. If we're in the center, but we're not in the plane of the loop, like we're sort of above or below the loop, the magnetic field will change. This is really only exactly at the center. All right, I want to give you one more result. And then we'll move on to a different topic. So let's also state the results for the magnetic field due to a long, straight current. All right, so what we'll imagine is we've got this straight wire and it's carrying some current. Well, why not make the current to the left? And then the question is, if we are a distance r away from that wire, what is the magnetic field at P? And so you can use the same Biot-Savart law to do this calculation. This one's a little more technical, a little more challenging. So we're not going to do it in detail, and I'm not going to expect you to reproduce it, say, on a final exam. But I will tell you that for a detailed analysis, analysis using the Biot-Savart law, if you're interested, you can see OpenStax, University Physics, Volume 2, Section 12.2. Okay, and the result is the following. So B is going to be equal to mu naught I over 2 pi r. Okay, here we go. Look at that. So if you look at the top, the current loop is mu naught I over 2r. For the long straight wire, it's mu naught I over 2 pi r. So there's only a difference of the factor of pi. And to get the direction, we could just use the right-hand rule. Remember, we had a right-hand rule for finding the direction of magnetic fields due to currents. We put our thumb of our right hand in the direction of the current, and our fingers curl around to give the direction of the field. And so at point P, my fingers above the wire are pointing into the screen. And so in this case, we have a magnetic field B that is into the screen. So we can see the tails of the feathers of the arrow that's flying away from us. And so this is into the screen in this case. Okay, good. So the other thing that I want to do today is we now have found that moving charges or currents create magnetic fields, and we have some ways to calculate what those magnetic fields are. We think back to point charges, and they created electric fields. And those electric fields that they create could then go exert forces on other charges. We're going to do a similar thing here. We now know that moving charges or currents create magnetic fields, and those magnetic fields can then go exert forces on other moving charges or other currents. Okay, so we'll start kind of a new topic here. So this is the force on a moving charge is what we'll start with, due to a magnetic field B. Okay, so let's imagine that we have a region of space where we have a magnetic field. I'm going to draw the magnetic field coming out of the screen. So here's all the little arrowheads, and that represents some magnetic field. Maybe it's a uniform magnetic field coming out of the screen. And then we're going to put a charge in there, and our charge is going to be moving with some velocity v at this moment. And we'll say that this is a positive charge, so Q is greater than 0. So the results that we're going to write down is just purely based on experimental observations. So if we set this up, we could, for example, establish this magnetic field, we fire a charge through it, and then we look at the force that that charge experiences. Maybe what we would have to do is measure its acceleration, and then if we know the mass of whatever that particle is, then we could calculate that force. So observations. If we actually set this up and did the experiments. So the first observation would be that if the velocity of the charge was 0, so it's just sitting there stationary, there would be no force at all. So only moving charges experience a force in a magnetic field. Okay. So then we say, okay, we're going to look at only charges that are moving. I fire a charge in with speed v, and I measure its force. And then I fire a charge in with twice that speed, and the force would be twice as big. If I fire a charge with half the speed, the force would be half as big. And so that tells us that the magnitude of the force is proportional to the speed. Okay. Observation 2. Now what we're going to do is we're going to keep the magnetic field the same, and we'll keep the velocity the same, but we'll fire charges of different values of Q. So if we double Q, the force is twice as big. If we cut Q in half, the force gets cut in half. So the force changes in proportion to the value of Q. So F, the magnitude of the force, is proportional to Q. All right. Observation number 3. We could now keep the charge the same, keep the velocity the same, but increase or decrease the strength of the magnetic field, and we would find that the force is proportional to the strength of the magnetic field. So the force is proportional to proportional to the magnitude of the magnetic field. So F is proportional to B. All right. Now, there's a more subtle observation, just like we had kind of a subtle observation for the strength of the magnetic field created by a moving charge. The force is going to depend on the relative direction of the velocity and the magnetic field. So the value of the force depends on the angle between V and B. Okay, so it's the sine of the angle. So if I had a velocity in one direction, say V, and then I had a magnetic field in some other direction, B, then the angle that matters is this one. So just like before, what we found is that if I had a moving charge creating a magnetic field, the magnetic field was a maximum at a position that was perpendicular to the velocity. And that's because the sine of 90 degrees is equal to 1. It's the maximum value of the sine. So F is a maximum when V is perpendicular to B, and F is equal to 0 when V is parallel to B. So this would be theta is 90 degrees, and this would be theta is 0 degrees. Okay, so if we combine all of these observations, then we would say, look, the magnitude of the force is, well, what did we say? It is proportional to Q. It's proportional to V. It's proportional to B. And it's proportional to the sine of the angle. Now, in principle, there could be like a constant of proportionality, like a mu naught or something like that. But it turns out that for this case, the constant of proportionality is just 1. So this is exactly the magnitude of the force acting on a charge moving through a magnetic field. VB sine theta. What's a nicer way of expressing VB sine theta? What did we say about cross products? A cross B is AB sine theta. So V is a vector, B is a vector, and so we could express VB sine theta in terms of V cross B, right? And so we could say the total force, which includes direction information, is Q V cross B. And this is the force acting on a charge moving through magnetic field B. Okay, so we have about 10 minutes left, and what I want to do is I want to do one interesting example. And the simplest thing we could do is we could have a charge moving through a uniform magnetic field. So B is a constant, and we'll make the charge move perpendicular to the magnetic field so that V cross B is VB sine theta, and theta will be 90 degrees. So the sine of 90 will just be 1. It's the simplest possible example, but it's actually pretty interesting. It's a nice one. So the simplest example is a charge moving perpendicular to a uniform magnetic field. And so we'll go back and we'll draw the same picture that we had. So we started with this picture of a magnetic field coming out of the page. And so we'll draw it something like this. And so this is the magnetic field. And we'll keep our charge Q. So let me see, what do I want to do? V cross B. Okay. All right, so that's fine. I'm going to move my charge up here a little bit. So we'll put Q over here and we'll have a velocity like this. Okay, so let's see what would happen qualitatively. What would be the direction of this force? Here, I'll write down the expression. So the force on our charge is QV cross B. All right, so at this moment, what is the direction of the force if we did B cross B? Somebody tell me. B is out of the screen and V is to the right. The force has to be perpendicular to both the velocity and the magnetic field, and so it's either up or down. So someone in the chat says up. What do you think? Yeah.
If it is a positive charge, then we down.
Yeah, so yeah, let's say it is a positive charge. So we have one vote for up and one vote for down. So V cross B. So B is to the right, and then B is pointing out of the screen. And so my thumb points down and the force is down. So at this moment, the force is downwards. Okay, well, so if the force is downwards, then there must be an acceleration downwards, and this thing is going to follow some kind of path that is maybe something like this, right? It's always moving a bit to the right, but it's moving more and more down more often. And so eventually we get to a point over here where maybe now, here, let's do kind of an intermediate point here. So now at this moment, the velocity is in that direction. So which direction of the force? Well, right-hand rule says B is in kind of slope down. B is still out of the page. And now my thumb kind of points something like this. So the force is doing something like this. So every time the charge changes its direction, the direction of the force changes a little bit. And so this would follow a path that would do something like this. And now we're over here. V is down, B is still out of the page, and now the force is to the left. And you can see what's happening. What type of motion is this charge undergoing? Circular motion. And so you could keep doing this type of argument, and the charge would follow a circular path where the force would always be perpendicular to its velocity, and it would always point towards the center of the circular path that it follows. Okay, so what we can say then is charges moving through a uniform magnetic field undergo circular motion. If the charge was negative, what would be different? It would just be a circular loop, but it would loop in the opposite direction. Okay. All All right, let's quickly write down the magnitude of the force. So the magnitude of the force would be equal to QVE sine theta, but theta is 90 degrees. So sine of theta is going to be 1. So therefore, the force, is equal to QVB. And that must be equal to the mass times the acceleration. But for an object moving in a circle, what's the acceleration equal to? What do you call the acceleration for something going in a circle? It's the centripetal acceleration, and the centripetal acceleration is equal to what? Somebody must know. Yeah. V squared over R. Okay, that's exactly what it is. V squared over R, where R would be the radius of the circle. So this is the centripetal acceleration. And so then what we have is QVB is equal to mv squared over R. We could cancel one factor of V. And if we solve for R, we would say R is going to be equal to what? mv divided by QB. This is the radius of the circular motion. Okay. Let's do one more thing. The time for the charge to complete one revolution is, so T, this is going to be the period of the motion. So one revolution occurs in time T. How would we calculate that? Well, we could take the total distance traveled, 2 pi r, divided by the speed that the particle is moving. Okay, so that's just 2 pi divided by v. And then let's see, r we just calculated. So for r, we use this result, mv divided by qb. And kind of an interesting thing happens here. The speed drops out. And so the period is 2 pi m divided by qb. And let's see. Yep, that's what I had. So this is the period of the circular motion. One thing that's interesting is that this is independent of V and R. You might have guessed that, well, particles that are moving faster will complete their revolution in a shorter time. Why doesn't that happen? It doesn't happen because particles that are moving faster have a larger radius. And so those two effects exactly cancel out. Here is a period that doesn't depend on the radius of the motion. This is kind of similar to what we were talking about in the very first lab with the pendulum. The pendulum, we found that if we increase the amplitude of the motion, then the period changed a little bit. Here, we have something where the size of the circular orbit does not affect the period of the motion. Okay, good. Thanks very much. What we'll do next time on Monday is we'll talk about what you're going to do in lab number 8.